Okay, so this is my first challenge problem video, and the first challenge problem is to integrate this function, which is not terribly difficult. This is probably one of the easier challenge problems. So obviously when we look at this problem, we can't actually start, right? Like it's like we don't have any standard integrals, we don't have any direct substitutions that come to mind, right? But we do know a relationship that's kind of important, right? We know that if, for example, theta is equal to sine inverse of x, then therefore sine theta is equal to x, right? And this relationship that we learned, in trigonometry is really, really important in order to solve this problem. So what we do is we start off by letting theta equal sine inverse of x. Now, why do we do this? It's essentially because every time you take sine inverse of a function, you're actually finding an angle, right? So you just let the angle theta equal sine inverse of x. So again, by taking sine on both sides, so sine theta is equal to sine of sine inverse of x, and then using the inverse property of sine, which says that sine of sine inverse is nothing. So sine theta is equal to x. So from this we can actually make substitutions. So initially we can see that we can make theta sine inverse of x. But what else can we do? We need to figure out a substitution for dx. So how are we going to figure out a substitution for dx? Well, obviously we're going to start here and we're going to take the derivative, right? So by taking the derivative on both sides, I don't know what's happening. Yeah, so by taking the derivative on both sides, we have d theta is equal to 1 over square root of 1 minus x squared. Now everybody knows the derivative of sine inverse of x is 1 over 1 minus x squared dx. Now you see here we said previously that x is equal to sine theta, right? So what we can do is we can actually substitute or change this x squared into sine theta squared. So this becomes 1 over square root of 1 minus sine squared of theta dx. Okay, so now we know by our trigonometric properties that 1 minus sine squared of theta becomes cos squared of theta. So this is square root of cos squared theta dx, and the square root of cos squared theta, this ends up being 1 over cos theta dx. So therefore we find an expression for dx, and dx is equal to, well, cos theta d theta. So now we have an expression for sine inverse of x, which is theta, and we also have an expression for dx. So now we can actually solve this problem. So now what we're going to do is, when we have the function sine inverse of x whole squared dx, we're going to change dx for cos theta d theta, and we're going to change sine inverse of x for, there's a squared here, sorry, for theta. So what ends up happening is we end up with theta squared times by and cos theta d theta. So now our function is integrate theta squared cos theta d theta. Now this is more doable than the previous question, right? The one where we couldn't make any direct substitution. So looking at this, the only way we can know, or the only way we can do this, is by parts. So we're going to use by parts, okay? Because we can see we have two separate functions multiplying to each other that have no correlation to one another. So definitely using by parts is our only option, right? So therefore, we know that in by parts, the integral of u v prime is equal to u v minus the integral of u prime v. Or sometimes some people write it the other way around, right? It doesn't actually matter how you write it, it's the same thing. Okay, so essentially what this means is we have to select one to be the derivative and one to be our non-derivative. So what we're gonna do, or I'm gonna do, is I'm gonna let u prime equal cos theta, and I'm gonna let v equal theta squared. So if u prime is equal to cos theta, then u is equal to the integral of cos theta d theta, which is sine theta, right? And v, the derivative of v is v prime, which is 2 theta, right? So now what we can do is we can make direct substitutions once we have all this into our by parts formula, right? So we have integral of theta squared cos theta d theta is equal to uv, so this is theta squared multiplied by sine theta minus the integral of 2 theta, right? V prime, sorry, I'll do u first. So u is sine theta times by v prime, which is 2 theta, right? D theta. So at this point, we're at theta squared times sine theta minus the integral, and we can take this constant out, obviously, just to make this equation a little bit simpler. So it's theta sine theta d theta. Well, again, now we have another problem because we have another function multiplied by another function. So at this point, what we can do is by parts again, right? So we end up with, now, in this point, I'm going to select this to be my u, and I'm going to select this to be my v prime. So using the same formula above, we know that, well, v is going to be minus cos theta. So we have theta times by minus cos theta, because if v prime is sine theta, then v is minus cos theta, right? Because it's the integral of sine theta, right? Now, we subtract this by the integral of u prime v. Well, u prime v is integral of u prime, which is 1, because the integral of theta is 1. I mean, the derivative of theta is 1. And the v prime, which we said before, is minus cos theta. So we have minus cos theta d theta, right? Because obviously 1 times by minus cos theta d theta is just minus cos theta d theta. So at this point, we're left with nothing ugly, right? And so we have theta squared times by sine theta minus 2 open bracket, and we can simplify this to minus theta cos theta, and the minus can cancel, so we have plus integral of cos theta d theta. And at this point we have theta squared sine theta minus 2 integral of minus theta cos theta, and then the integral of cos theta is sine theta, so plus sine theta, and now we can just add our plus c at the end, right? Initially, technically, we should be adding multiple plus c's, but really it does not matter, right? So here, theta squared sine theta plus, because minus 2 times by minus theta, plus 2 theta cos theta minus 2 sine theta plus c. Now, obviously, we want to integrate this in terms of x, right? Because that's our original function. So we can't actually have them in terms of theta and say we're done, right? We have to actually change them back. So initially, we said that theta is equal to sine inverse of x. So here, this theta squared here becomes sine inverse of x whole squared. And we said that sine theta is equal to x. So we can just change that 2 times x. Plus, now 2 and theta again is sine inverse of x cos theta. Now here's the problem, right? But we know sine theta, but we don't know cos theta. Well, let's figure out cos theta. So we know sine theta is equal to x on 1. And sine theta is also opposite over hypotenuse. So by drawing a right angle triangle, we know the opposite is x and the hypotenuse is 1. Using Pythagoras' theorem, this becomes square root of 1 minus x squared, right? So what we do is, by looking at this, we can say that cos theta, okay, obviously here's theta, is the opposite angle over, the adjacent angle over the hypotenuse, right? So in this case, the adjacent angle is square root of 1 minus x squared on 1, square root of 1 minus x squared, right? So cos theta is square root of 1 minus x squared. So now we can replace this with times square root of 1 minus x squared. And then minus 2 times by and sine theta was x plus c. So our final answer is sine inverse of x whole squared, or x sine inverse of x whole squared, plus 2 square root of 1 minus x squared sine inverse of x minus 2x plus c. And this is actually how you integrate challenge problem 1.